Katie France.
I'm Garrett O'Toole.
And today we are going to be learning about the physics of music.
I brought out my guitar to play an Eric Clapton song called After Midnight, and I'm going to compare that to the pure tones and some Fourier analysis and break that down for you. Hi there, my name is Garrett O'Toole, and today I will be talking about the physics of music and how it all relates back to this guy, the electric guitar. Well, for starters, as you can see, this isn't an acoustic guitar. What makes an acoustic guitar different from an electric guitar is an acoustic is actually a hollow body, and that's what actually makes the sound resonate inside. It resonates inside the body, that's why it has that sound hole. Electric guitars have different things called pickups, which mine has two humbucking pickups, which is basically they're two single magnetic coils wound together. And what the double coil offers instead of like a single coil, what a Stratocaster would offer, is the two actually cancel certain parts of each other out. So what it's going to do is minimize hum, and I'm not going to get as much feedback. As you can see, there's not much buzz, but if I turn my volume up, there's still not that much buzz, and I'm all the way up. But what's cool about this guitar is I can actually make it into single coil pickup by pulling on the knobs here. And as you can see, it might be a little hard to hear there, but there's more buzz coming from there than there was with the humbucking pickup. So I'm going to go back to my standard here. Another thing that's so different on an electric guitar compared to an acoustic guitar is since the electric guitar has pickups, the sustain is so much longer and greater and everything else that you would think. An acoustic guitar, since the inside is resonating, it's actually dampening its own sound. An electric guitar, there's nothing to dampen that sound since it's a hollow body, so I can just play one of these. And as you can see, it's still going to go for a really long time. Even if I add some effects, like a vibrato, just add some dynamic flair. And another thing, since it's so sensitive, what you can actually do are these things called hammer-ons and pull-offs. So a hammer-on is you're just going to play a note and then hammer on to the next note. So for instance, or a pull-off is you're pulling off of one note onto another. And as you can see, I only played it once, so it was basically just the action of me picking my finger up and kind of like pulling the string, and that was as clear as day coming through the speaker. The biggest thing why pickups are such a big deal in an electric guitar is that what they do is they change the sound that's being emulated from the guitar. So since there's a magnetic field, it's actually magnetizing the strings, and that's what enables to pick up that sound, and it changes the form of that sound. So instead of hearing an audible sound, the guitar picks it up as a voltage source, basically, and that's led through the guitar, through the circuitry, out of the quarter inch, and then into your amp or your effects pedal. For me, I actually have an effects pedal right here that I will be switching off sounds, and the effects pedal is something that every guitar player absolutely needs to have. The big thing about pedal boards and why they're so sought after is the distortion effects that you can put on your guitar. Me, I have a Fender Mustang floor, and everything is digital and preset, so I can switch through something here to a little more cleaner sound to really dirty, heavy, muddy, high gain sound. So the big thing about this is early artists like Hendrix, mainly Hendrix really popularized the really heavy distortion. What the really heavy distortion does is maxes out the levels at which that sound is being amplified. So it actually sounds obviously distorted, number one, but number two, it adds like a really heavy edge to it. And of course you can change that for whatever song you need. If you're going with like Party in the USA, you're not going to want to sound like to play that. Alright, so say we wanted to jam out to something like Miley Cyrus' Party in the USA, I don't know, off the top of my head. If you judge me, that's on you. It's such a catchy song, and I really don't care what you think. So you're going to want to switch from something a little more distorted to something cleaner, obviously, because that's just not how Miley rolls as opposed to Hendrix. Say we're going to go into this. Turn my sound on, that would be helpful. And there you go. Now that offers a night and day difference from the heavier distorted sound. Again, let me turn my volume on here. Right off the bat, major difference. Alright, so as you can see, the guitar has two pickups, and it actually offers 3 possible positions on my guitar. Normally on Stratocasters you can get up to like 5 positions, which is a mixture of the two. So let's start in the rhythm section, which is the neck pickup, aka the highest one possible. This one really offers a nice way to get like a really clean, jazzy, warm, and bright sound. I use it for, like I said, really jazzy stuff if I'm in the mood, so it'll sound something like... So again, and that also depends on whatever like distortion effects you're using, so as you can tell there wasn't that much on there. Alright, now let's switch to the middle position. So if the neck is the high end, really warm, really bright, the bridge is going to be the low end, which is like the really gritty, really heavy, like hard rock sound, which is normally everyone's favorite. So the middle is going to be a mixture of the both. This is your middle of the road. So again, same thing. Here we go. Now again, I didn't change sounds or anything, so you can tell that there was a little more edge to that one. And again, playing the same thing, same sound around the bridge. As you can tell, major difference from the other two, especially the neck pickup. Alright, so of course this year we learned about major things like harmonics and wavelength and everything. And the guitar string is your wavelength. There's a really complicated formula to solve for how fast the wave is actually being produced off of the string. I'm not going to go into that, but really what I do want to focus on is the fact that you can prove that there are different harmonics that exist within the string. So obviously if you just play like an open E string, that's the fundamental frequency. So that's the one that has, it's not even a full wave, it's half the wave. It's just that one arc. You kind of have to imagine the rest of it goes on underneath. That, again, fundamental frequency. So the second harmonic we can actually access by using these things called pinch harmonics. And like the resonance lab, it has to be at a specific point on the neck where the wavelength is just long enough where you can pull the node out and you'll be able to hear it. On guitars, all guitars actually, the second harmonic resides in the 12th fret. And what you do is you play that fundamental frequency, so just the open string, open low E string, and I'm gonna gently tap it, and it's going to pull the second harmonic out of it. So let's take a listen. You could hear that pitch change there. Again, let me get that one more time. There's that sound as opposed to the fundamental, which was... And then, if we really wanted to, we could access the third harmonic, which is up on the 5th fret. So again, first fundamental, second harmonic, and then third harmonic. And that's how you do it. So that'll prove that you're pulling the nodes out and accessing the harmonics. And that works on every string of the guitar. The next big thing, I touched on this earlier, is adding some artistic flair, which you hear, all across the radio and all across your favorite song. So I mentioned vibrato earlier, which is basically just vibrating the string back and forth more than it already is. Since it's a string, we know already that it oscillates back and forth, which is what produces that sound wave. So if you add some vibrato, again, vibrato, vibrate, I'm just going to wiggle the string back and forth, and that's going to ultimately shift the pitch against what it naturally wants to do. So, and of course, since I'm moving it back and forth, it's going to dampen out, so the sustain isn't going to be there as long. It acts as a whammy bar going back and forth. So if I change the tension of the string, I'm ultimately going to change properties like wavelength, which is going to affect the velocity, which then affects like the sound being produced, which is what you hear. So I touched on hammer-ons, pull-ons, and now vibratos. So I'm going to get into a song. It's one of my favorite to play. It's an Eric Clapton classic called After Midnight. He uses all of this all across as well as heavy distortion in the verse, intro, and solo. So let's get into that now, and then I'll be able to break it down afterwards and analyze it for me jam out on that one. Now you know why that's one of my favorite songs to play. It's just got such a nice groove to it, and I can use so many different effects on it to make it sound really nice. Alright, so now what we're going to do is we're going to analyze different parts of the songs using some Fourier analysis and check out their own sound waves, compare and contrast them, and then work on some calculations just to prove how much physics goes into playing guitar.
Because there are so many factors in the song as a whole, we can analyze components of the song by looking at the pure tones that make up the song. And using pure tones, we can use the equation we are familiar with from class, which is velocity equals wavelength times frequency. We immediately know the frequency of the tone because it is given with the tuning fork. Additionally, the velocity is the same for all the pure tones because it is the velocity of sound, which is easily calculated by multiplying the current room temperature in Celsius by 0.6, then adding 331. Since we know two variables of a three-variable equation, we can manipulate velocity equals frequency times wavelength and make it wavelength equals velocity divided by frequency. Keep in mind when looking at the graphs of pure tones, there may be some irregularities, but they are only due to impurities in the tuning fork. The first tone we are looking at is D sharp. This tone has the lowest frequency, which is smaller than the speed of sound. This results in being the only tone with a wavelength greater than 1 meter. The next tone we are looking at is A. This note has the highest frequency of the 4 tones we collected, which results in a significantly lower wavelength. Now we are looking at the pure tone of F. This tone has a frequency that is closest to the speed of sound, which yields a wavelength extremely close to 1 meter. Lastly, this pure tone is G. It falls in the middle with a frequency in comparison to the other tones. Because of this, the wavelength is a median value of the other tones collected. The peak sound pressure occurs when all 6 strings are strummed for the chord. The lower peaks are when just the A string is played, which means the total amount of distortion effects is significantly lower than when all 6 strings are strummed, which ultimately affects the sound pressure. Even light distortion maxes out peaks for sound pressure analysis. More importantly, the bottom graph shows the amplitude and frequency of the waves. The higher amplitudes show a louder sound, which results from more notes happening simultaneously and stacking on top of one another. Same thing is happening here. You can see the majority of the graphs are really close together, which signifies the high frequency. Since there is a high frequency, that means the sound wave itself contains a ton of energy once all of the distortion effects go into it. Again, we are seeing here maxed out peaks of sound pressure and even amplitude. The vibrato and other effects that are on this sound is a direct cause of it.
I hope you enjoyed our lesson today.
That's it. I hope you learned something new and hopefully can apply that in real life.